How many stars are in the universe? It is one of the oldest questions humans have ever asked. And tonight, we are going to find out the answer together. If you have enjoyed this journey so far and want to continue exploring the cosmos with us, please take a moment to like this video and subscribe to the channel. It helps us bring more of these peaceful explorations to you. Now, let us begin. Picture yourself on a beach at night. The sand is cool beneath your feet. The waves whisper against the shore. And above you, the sky is filled with tiny points of light. Stars, thousands of them. Maybe millions, it seems. You reach down and pick up a handful of sand. The grains slip through your fingers, too many to count. And somewhere in your mind, thought forms. Could there really be more stars up there than grains of sand down here? This is not just a poetic idea. It is not just a beautiful thought to hold before sleep takes you. This is a real question that scientists have spent decades trying to answer. And the answer, when we finally reach it, will be almost too large to understand. But we will try anyway, because that is what humans do. We look up at the impossible, and we try to make sense of it. The claim you may have heard before is simple. There are more stars in the universe than grains of sand on all the beaches of Earth. Every beach, every coastline, every tiny island in every ocean, all that sand, all those countless grains, and still, there are more stars. It sounds impossible. It sounds like something made up to make us feel small. But as we will discover together, it is true. And the real number is even more astonishing than you might imagine. To answer the question of how many stars exist, we cannot simply look up and count. The universe is too vast. The stars are too many. Some are hidden behind clouds of cosmic dust. Some are so far away that their light has not even reached us yet. Some exist in galaxies so distant that we will never see them at all. So how do we even begin? The answer is that we start small. We start with what we can see. We start with our own galaxy, the Milky Way. This great spiral of stars that contains our Sun, our Earth, our entire solar system. If we can figure out how many stars are in our own cosmic neighborhood, then perhaps we can use that knowledge to estimate the stars in other galaxies. And if we can count the galaxies, then perhaps, just perhaps, we can arrive at a final number. It is a journey that will take us from the dust clouds of our own galaxy to the most distant edges of the observable universe. Along the way, we will encounter strange and wonderful things. Black holes, dark matter, the warping of space and time itself. But for now, let us simply settle into the journey. Let the numbers wash over you like waves. There is no test at the end. No need to memorize anything. Just listen and let the scale of the universe fill your mind. The Milky Way is our home. It is a barred spiral galaxy, which means it has long arms of stars that curve outward from a central bar of older, yellower stars. If you could see it from above, it would look like a giant pinwheel spinning slowly in the void. Our Sun sits about 2/3 of the way out from the center, nestled in one of the spiral arms. We are not in a special place. We are not at the center of anything. We are simply one star among many, in one arm among several, in one galaxy among billions. But how many stars are in our galaxy? This seems like it should be a simple question. After all, the Milky Way is right here. We live inside it. Surely we can just count the stars. But as with so many things in astronomy, the reality is far more complicated. The first problem is dust. The space between stars is not empty. It is filled with vast clouds of gas and tiny particles of dust. This dust blocks light. When you look toward the center of the Milky Way on a clear night, You are seeing a dense band of stars, but you are also seeing dark patches where the dust is so thick that it blocks the starlight behind it. These dust clouds hide many of the stars in our galaxy from our view. The second problem is distance. Stars that are farther away appear dimmer. Very distant stars in our galaxy may be too faint for our telescopes to detect at all, and stars in the far reaches of the Milky Way on the other side of the galactic center are almost impossible to see because all that dust and all those other stars are in the way. So astronomers have developed clever methods to estimate the star count. One approach is called the mass-to-light ratio. The idea is simple in concept, but tricky in practice. First, you measure the total mass of the galaxy. You do this by watching how fast stars orbit around the galactic center. Just like planets orbit the Sun because of its gravity, stars orbit the center of the Milky Way because of the gravity of everything inside their orbit. The faster a star moves, the more mass there must be pulling on it. By measuring these orbital speeds, astronomers can calculate the total mass of the galaxy. But here is where it gets interesting. Not all that mass is made of stars. Some of it is gas. Some of it is dust. And a lot of it, as we will discuss later, is dark matter, a mysterious substance that we cannot see but that has gravity. So astronomers have to subtract out the gas and dust, and they have to account for the dark matter. What remains is the mass that should be locked up in stars. Then comes the second part. Astronomers look at how much light the galaxy produces. If they know how much light a typical star gives off, they can divide the total light by the light of an average star to get an estimate of how many stars there are. But stars are not all the same. Some stars are huge and bright, giving off thousands of times more light than our Sun. Some are small and dim, giving off only a tiny fraction of the Sun's light. Most stars in the universe are actually quite small. Red dwarfs, they are called. They are cooler and dimmer than our Sun, and they outnumber the larger stars by a huge margin. So the calculation becomes more nuanced. Astronomers have to account for the distribution of star sizes. They use what is called an initial mass function, which is basically a formula that tells them how many stars of each size they should expect. When they put all of this together, the mass of the galaxy, the light it produces, the expected sizes of stars, they arrive at an estimate. And that estimate is somewhere between 100 billion and 400 billion stars. Let us pause on that number for a moment. 100 billion to 400 billion. The range is large because there is so much uncertainty. We cannot see all the stars. We are not sure exactly how much dark matter there is. The calculations are estimates, not exact counts. But even the low end of that range is staggering. 100 billion stars in our galaxy alone. To put that in perspective, if you try to count to 100 billion, counting one number every second without stopping, it would take you more than 3,000 years. You would never finish. Your great-great-great-grandchildren would never finish. 100 billion is not a number the human brain is designed to understand. And that is just our galaxy. That is just the Milky Way. There are other galaxies out there. Many, many other galaxies. For most of human history, people did not know that other galaxies existed. They saw fuzzy patches of light in the night sky and called them nebulae, which just means clouds. Some astronomers thought these nebulae were gas clouds within our own galaxy. Others wondered if they might be something more. Island universes, some called them, separate collections of stars far beyond the Milky Way. The question was not settled until the 1920s, when an astronomer named Edwin Hubble used a powerful telescope to look closely at one of these nebulae. the Andromeda Nebula, he found something remarkable. He found a type of star called a Cepheid variable. These stars pulse in brightness in a very regular way, and the rate of their pulsing is related to how bright they actually are. By comparing how bright the star appeared to how bright it actually was, Hubble could calculate how far away it was. The answer shocked the world. The Andromeda Nebula was not a cloud of gas within the Milky Way. It was a separate galaxy, millions of light years away. It contained billions of its own stars. Our galaxy was not alone. It was one of many. Once astronomers knew what to look for, they began finding galaxies everywhere. Spiral galaxies like our own, elliptical galaxies, great spherical collections of older stars, irregular galaxies with no particular shape, dwarf galaxies, small companions orbiting larger galaxies. The universe, it turned out, was filled with galaxies. But how many? For decades, the best estimate was around 200 billion galaxies in the observable universe. This number came from surveys like the Hubble Deep Field. In 1995, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky. They kept the camera open for days, collecting light. When they developed the image, they found something astonishing. That tiny patch of sky, no bigger than a grain of sand held at arm's length, contained thousands of galaxies. Each one was a vast collection of billions of stars. By extrapolating from this small sample to the entire sky, astronomers estimated that there were around 200 billion galaxies in the observable universe. 200 billion galaxies, each containing an average of about 100 billion stars. The total number of stars would be around 10 to the 22nd power. That is a 1 followed by 22 zeros. In other words, 100 sextillion stars. But in 2016, that estimate changed dramatically. A new study looked at the data more carefully. It considered very small, very faint galaxies that earlier surveys had missed. Galaxies at the edge of detection. Galaxies so dim that they barely registered. When these were accounted for, the new estimate was not 200 billion galaxies. It was 2 trillion galaxies. 10 times more than the previous estimate. This revision changed everything. If there are 2 trillion galaxies, and each one contains an average of 100 billion stars, then the total number of stars is around 2 times 10 to the 23rd power. That is 200 sextillion stars. Or to write it out, 200,000 million stars. Let us pause here again. 200 sextillion is a number that has no meaning to the human brain. It is not a number we can visualize or comprehend. It is just too large. So let us try to bring it down to something we can almost grasp. Imagine counting stars at a rate of 1 per second. Not just for a day or a year, but for the entire history of the universe. The universe is about 13.8 billion years old. If you had been counting stars since the Big Bang, 1 every second, you would have counted about 400 quadrillion stars by now. That sounds like a lot, but it is less than 1/1,000,000th of 1% of the total. You would need to count for billions of times longer than the universe has existed to count all the stars. Or consider the sand comparison again. Scientists have estimated that there are roughly 7.5 times 10 to the 18th grains of sand on Earth. That is 7.5 quintillion grains. The number of stars at 2 times 10 to the 23rd is about 30,000 times larger. For every grain of sand on every beach, in every desert, on every riverbank, there are 30,000 stars in the observable universe. This is the scale we are dealing with, and we are only getting started. To understand how we arrived at these numbers, we need to look more closely at the tools astronomers use. The most famous of these is the Hubble Space Telescope, launched in 1990. Hubble has transformed our understanding of the universe. Orbiting above the blurring effects of Earth's atmosphere, it can see objects fainter and more distant than any ground-based telescope. The Hubble Deep Field images revealed thousands of galaxies in a tiny patch of sky. Later, Hubble took even deeper images. The Ultra Deep Field, released in 2004, exposed the same patch of sky for nearly 1 million seconds. That is almost 12 days of total exposure time. The resulting image showed nearly 10,000 galaxies, some of them so distant that their light had been traveling for over 13 billion years. We were seeing these galaxies as they were just a few 100 million years after the Big Bang. But as powerful as Hubble is, it has limitations. It observes mainly invisible light and some ultraviolet and infrared. Very distant galaxies have their light stretched by the expansion of the universe, shifting from visible wavelengths into the infrared. To see the most distant galaxies, we need a telescope designed specifically for infrared observation. That telescope is the James Webb Space Telescope, launched in December 2021. Webb carries a mirror over 2.5 times larger than Hubble's, and it is optimized for infrared light. In its first year of operation, Webb has already revealed galaxies more distant than any seen before. It has shown us that galaxies formed earlier and more abundantly than we expected. With each new image, our estimate of the total number of stars may increase. But counting galaxies is not the same as counting stars. Each galaxy is different. Some are giants like the Milky Way, or even larger. The Andromeda Galaxy, our nearest large neighbor, may contain over 1 trillion stars. Some galaxies are even bigger. IC 1101, one of the largest known galaxies, might contain over 100 trillion stars. But most galaxies are small. Dwarf galaxies may contain only a few billion, or even a few million stars. And there are far more small galaxies than large ones. So when astronomers estimate the total number of stars, they have to account for this variety. They use models that predict how galaxies are distributed by size. They multiply the number of galaxies by the average number of stars per galaxy. And they arrive at that staggering number, somewhere around 10 to the 23rd, or 2 times 10 to the 23rd stars in the observable universe. But there is a complication. A beautiful, strange complication that makes the counting even harder. When we look at distant galaxies, we are not seeing them as they are now. We are seeing them as they were billions of years ago. Light travels fast, about 300,000 kilometers per second. But the universe is so vast that even light takes time to cross it. The light from the Andromeda Galaxy takes about 2.5 million years to reach us. The light from the most distant galaxies visible to Hubble has been traveling for over 13 billion years. This means that when we look at a distant galaxy, we are looking back in time. We are seeing that galaxy as it was when the light left it, not as it is now. A galaxy that appears small and young in a deep field image may have grown into a large, mature galaxy by now. Or it may have merged with another galaxy. Or it may have been torn apart by gravitational forces. We cannot know its current state because its current light has not reached us yet. This is called look-back time. It adds a layer of uncertainty to our star count. The galaxies we see at the edge of the observable universe are ancient. They formed when the universe was young, when stars were made from nearly pure hydrogen and helium. The first generation of stars, called population 3 stars, may have been very different from the stars we see today. They may have been much larger, much hotter, and much shorter lived. Some may have exploded as supernovae within just a few million years, seeding the universe with heavier elements. When we count stars in distant galaxies, we are counting stars as they were billions of years ago. Many of those stars no longer exist. They have burned out or exploded, but other stars have formed since then. The star count in those galaxies today would be different from what we observe. There is another phenomenon that helps and complicates our counting. It is called gravitational lensing. Einstein predicted that massive objects bend the fabric of space and time. This means that light passing near a massive object, like a galaxy or a cluster of galaxies, will be bent. If a distant galaxy happens to be behind a massive cluster, the cluster can act like a lens, bending and magnifying the light from the distant galaxy. Gravitational lensing allows us to see galaxies that would otherwise be too faint to detect. The light from these background galaxies is stretched and distorted, sometimes forming arcs or rings around the foreground cluster. By analyzing these distorted images, astronomers can learn about the distant galaxies and the mass of the lensing cluster. This effect reveals galaxies that would otherwise be invisible to us. It extends our reach deeper into the universe, but it also means that our surveys are biased. We see more galaxies in directions where there happens to be a massive cluster acting as a lens, and we may miss galaxies that are not behind such lenses. The true number of galaxies, and thus the true number of stars, may be even higher than our estimates. Now, let us turn to something strange and invisible. Something that makes up most of the matter in the universe, but that we cannot see or touch. Dark matter. When astronomers first measured the speeds at which stars orbit within galaxies, they found something puzzling. The outer stars were moving too fast. According to our understanding of gravity, stars farther from the galactic center should move more slowly, just as outer planets in our solar system orbit more slowly than inner ones. But that was not what astronomers observed. The outer stars moved almost as fast as the inner ones. There were two possible explanations. Either our understanding of gravity was wrong at galactic scales, or there was more matter in galaxies than we could see. Most astronomers settled on the second explanation. There must be a vast amount of invisible matter surrounding galaxies, providing the extra gravity needed to explain the fast-moving outer stars. This invisible matter came to be called dark matter. We still do not know what dark matter is. It does not emit light. It does not absorb light. It does not interact with normal matter except through gravity. Various particles have been proposed as dark matter candidates, but none have been definitively detected. And yet, the evidence for dark matter is overwhelming. It shapes the structure of galaxies. It determines how galaxies cluster together. It influences the cosmic microwave background, the faint glow left over from the early universe. Dark matter is important for our star count because it affects the total mass of galaxies. Remember, one way to estimate the number of stars is to measure the mass of a galaxy and then figure out how much of that mass is in the form of stars. But most of a galaxy's mass is dark matter, not stars. In a typical galaxy, dark matter outweighs normal matter by about 5 to 1. Stars, planets, gas, and dust make up only a small fraction of the total mass. This means that when we estimate star counts from galactic masses, we have to carefully subtract the dark matter. If we overestimate the dark matter, we will underestimate the stars. If we underestimate the dark matter, we will overestimate the stars. The uncertainty in our dark matter models translates into uncertainty in our star count. And then there is dark energy. If dark matter is strange, dark energy is stranger still. In the late 1990s, astronomers made a surprising discovery. They were studying a type of exploding star called a Type Ia supernova. These supernovae all have about the same intrinsic brightness, which makes them useful for measuring cosmic distances. By observing how bright they appear, astronomers can calculate how far away they are. When astronomers measured the distances to distant supernovae and compared them to how fast those supernovae were receding due to the expansion of the universe, they expected to find that the expansion was slowing down. Gravity should be pulling everything together, causing the expansion to decelerate over time. But that was not what they found. The expansion was speeding up. Something was pushing the universe apart, overcoming the gravitational attraction of all the matter in the cosmos. This mysterious something was called dark energy. We understand it even less than dark matter. It appears to be a property of space itself, a kind of energy that causes space to expand faster and faster. Dark energy makes up about 68% of the total energy content of the universe. Dark matter makes up about 27%. Normal matter, the stuff you and I and the stars are made of, accounts for only about 5%. Dark energy affects our star count in a subtle but important way. It determines the volume of the observable universe. The observable universe is the region from which light has had time to reach us since the Big Bang. As the universe expands, this volume increases. But if dark energy is causing the expansion to accelerate, then distant regions are receding from us faster than before. Eventually, galaxies that are now visible will recede so fast that their light will never reach us. They will slip beyond the cosmic horizon. Right now, the observable universe has a radius of about 46 billion light years. This might seem strange, since the universe is only about 13.8 billion years old. How can we see objects 46 billion light years away if their light would need 46 billion years to reach us? The answer is that space itself has been expanding while the light was traveling. An object that was much closer when its light was emitted is now much farther away because space has stretched. The light we receive is ancient, from when the object was closer. But by now, that object is far beyond where its light originated. All the stars we count are within this observable universe. But what lies beyond? This brings us to one of the deepest questions in cosmology. The observable universe is not the whole universe. It is simply the part of the universe we can see. Beyond the cosmic horizon, there is more. Perhaps much more. Perhaps infinitely more. Most cosmologists believe that the universe extends far beyond what we can observe. This belief is based on the theory of cosmic inflation. According to inflation, the universe underwent a period of incredibly rapid expansion in the first tiny fraction of a second after the Big Bang. In this brief moment, the universe expanded by a factor of at least 10 to the 26th, perhaps by a factor of 10 to the 100th or more. The numbers are almost meaningless at this scale. If inflation happened, then the universe is vastly larger than the part we can see. The observable universe would be just a tiny bubble in an ocean of space. Beyond our horizon, there would be more galaxies, more stars, more everything. And the total number of stars in the entire universe would be far larger than the 1 or 2 times 10 to the 23rd that we estimate for the observable universe alone. How much larger? We do not know. It could be 100 times larger, 1,000,000 times, a Google times, or it could be infinite. Some versions of inflation suggest that the universe is truly infinite in extent, containing an infinite number of galaxies and an infinite number of stars. In an infinite universe, our estimate of stars is meaningless. You can't say there are 100 sextillion stars if the true number is infinite. But infinity is hard to think about. So let us return to the number we can estimate. The stars in the observable universe. Around 100 sextillion to 200 sextillion, depending on whose estimate you trust. A number so large that it defies all human experience and intuition. Let us try once more to bring this number into some kind of focus. Imagine you had a pile of rice. Each grain of rice represents one star. How big would that pile be? A single grain of rice is tiny, maybe 6 millimeters long. 100 sextillion grains of rice would fill a volume of about 400 trillion cubic kilometers. That is roughly the volume of a sphere 300,000 kilometers across. For comparison, the distance from the Earth to the Moon is about 384,000 kilometers. Your pile of rice, each grain representing one star, would stretch most of the way to the Moon. Or consider this: if you could travel at the speed of light, the fastest speed possible, it would take you about 100,000 years to cross our galaxy, and our galaxy is just one of 2 trillion galaxies in the observable universe. The distances involved are beyond comprehension, the number of stars even more so. There is something almost comforting in these numbers, though. They are so large that they stop feeling threatening. They are so far beyond our everyday experience that they become abstract, like numbers in a dream. You do not need to fear the vastness of the universe. You do not need to feel small or insignificant. These numbers are simply what is. They are the reality we live in, whether we think about them or not. And there is a strange peace in accepting that reality, in letting it wash over you like starlight on a clear night. Now, let us look more closely at how these stars are distributed. The universe is not uniform. Stars are not scattered evenly across space like salt sprinkled on a table. They clump together. They form patterns and structures that span billions of light years. At the smaller scale, stars form in groups. Our Sun is a relatively solitary star, but many stars have companions. Binary star systems, where 2 stars orbit each other, are common. Triple and quadruple systems exist as well. Some stars are born in dense clusters. Thousands of young stars huddle together in a relatively small volume. Over time, these clusters may drift apart, their stars scattering into the wider galaxy. At the next scale up, we have galaxies. A galaxy is a gravitationally bound collection of stars, gas, dust, and dark matter. Galaxies come in many shapes and sizes. Spiral galaxies like the Milky Way have graceful arms wrapping around a central bulge. Elliptical galaxies are more uniform, great spherical or oval collections of older stars. Irregular galaxies have no particular shape, often because they have been disturbed by gravitational interactions with other galaxies. Galaxies themselves are not evenly distributed. They tend to cluster together in groups and clusters. Our own galaxy is part of a small group called the local group, which contains about 80 galaxies. The largest members are the Milky Way and the Andromeda Galaxy. Most of the others are small dwarf galaxies. The local group, in turn, is part of a larger structure called the Virgo supercluster. At the center of this supercluster is the Virgo cluster, a dense collection of over 1,000 galaxies about 50 million light-years away. The Virgo supercluster contains about 100 groups and clusters of galaxies, spread across a volume over 100 million light-years across. But even superclusters are not the largest structures. In recent decades, astronomers have mapped the distribution of galaxies across vast swaths of the universe. They have found that galaxies form enormous filaments and walls, surrounding great voids where few galaxies exist. The cosmic web, astronomers call it. If you could zoom out far enough, the universe would look like a sponge, with dense filaments of galaxies surrounding empty bubbles. The largest known structure is the Hercules Corona Borealis Great Wall, a filament of galaxies stretching about 10 billion light-years across. It contains billions of galaxies and countless trillions of stars. And yet, even this vast structure is just a small part of the observable universe. All of this structure matters for our star count, because stars are not distributed uniformly. There are more stars in dense galaxy clusters than in the voids between them. When astronomers estimate the total number of stars, they have to account for this clustering. They survey representative samples of the universe and extrapolate to the whole. Now let us consider the different types of stars that make up this vast population. Not all stars are alike. They vary enormously in size, temperature, brightness, and lifespan. Our Sun is a medium-sized star, a yellow dwarf in astronomical terminology. It has a surface temperature of about 5,500 degrees Celsius and will burn steadily for about 10 billion years. But most stars are smaller and cooler than the Sun. Red dwarfs are the most common type of star in the universe. They are less than half the Sun's mass, often much less. Their surface temperatures are around 3,000 degrees Celsius or lower, giving them a reddish color. Red dwarfs are so dim that not a single one is visible to the naked eye from Earth, even though the nearest stars to our Sun are red dwarfs. Red dwarfs may be small, but they are long-lived. Because they burn their fuel slowly, red dwarfs can shine for trillions of years. The universe is only about 14 billion years old, which means that every red dwarf that has ever formed is still shining today. None have yet burned out. In the far future, when larger stars have long since died, red dwarfs will be the only stars still lighting the cosmos. At the other end of the scale are the giants and supergiants. These are stars much larger and more massive than our Sun. They burn hot and bright, their surfaces reaching tens of thousands of degrees. A blue supergiant like Rigel in the constellation Orion is over 20 times more massive than the Sun and about 120,000 times more luminous. But such brilliance comes at a cost. Massive stars burn through their fuel quickly. A star like Rigel will live for only a few million years before exploding as a supernova. Between these extremes are stars of every size. Yellow stars like our Sun. Orange stars slightly smaller and cooler. Blue stars hotter and brighter. Each type has its own characteristics, its own lifespan, its own place in the cosmic ecosystem. When astronomers count stars, they have to account for this variety. The distribution of star sizes follows a pattern called the initial mass function. This function tells us that for every massive blue star, there are many more medium-sized stars like our Sun, and far more still small red dwarfs. If you picked a star at random from the universe, it would almost certainly be a red dwarf. These dim, cool stars dominate the cosmic census. This has implications for the search for life. Red dwarfs are so common that if even a small fraction of them have habitable planets, the total number of potentially life-bearing worlds would be enormous. But red dwarfs are also temperamental. Young red dwarfs tend to produce powerful flares that could strip away a planet's atmosphere. Whether life could survive around such stars is still an open question. Let us return now to the methods astronomers use to estimate star counts. We have discussed the mass-to-light ratio, which involves measuring a galaxy's mass and its light output, then calculating how many stars could produce that much light with that much mass. But there are other approaches as well. One method is direct star counts. For nearby regions of the Milky Way, astronomers can actually count individual stars. They take deep images of specific areas and count the points of light. By combining counts from many different directions, they can build up a picture of how stars are distributed throughout the galaxy. This method has limitations. It only works for nearby regions. As you look farther away, individual stars become too faint to detect. And in the direction of the galactic center, the stars are so densely packed and the dust so thick that distinguishing individual stars becomes impossible. Another method uses statistical analysis. Astronomers know the relationship between a star's color and its brightness. A blue star is typically brighter than a red star. By measuring the colors of stars in a given region and using this relationship, astronomers can estimate the distances to those stars. This allows them to construct a three-dimensional map of stellar distribution. Modern surveys have used this technique on a massive scale. The Gaia Space Telescope, launched by the European Space Agency in 2013, has measured the positions, distances and motions of nearly 2 billion stars in the Milky Way. This is only about 1% of the galaxy's total, but it provides an unprecedented view of stellar distribution. Gaia's data has refined our estimates of the Milky Way star count and structure. For galaxies beyond the Milky Way, different techniques are needed. One approach is to measure the total light output of a galaxy and then use models of stellar populations to estimate the number of stars. This requires assumptions about the age and composition of the galaxy's stars, but it provides reasonable estimates. Another technique is to study resolved stellar populations. In nearby galaxies, Hubble and other telescopes can distinguish individual bright stars. By counting these bright stars and using models of stellar populations, astronomers can extrapolate to the total number of stars, including the fainter ones that cannot be resolved. Gravitational microlensing provides yet another window into stellar populations. When a star in the foreground passes in front of a more distant star, the foreground star's gravity bends the light from the background star, causing it to briefly brighten. By monitoring millions of stars and watching for these brightening events, astronomers can estimate the number of stars that are too faint to see directly. All of these methods have uncertainties. They rely on assumptions about stellar populations, dark matter distributions, and the properties of galaxies. The estimates they produce are not exact counts, but educated guesses. That is why the range for stars in the Milky Way is so large, from 100 billion to 400 billion. And the estimate for the entire observable universe, around 100 to 200 sextillion, carries similar uncertainties. But even with these uncertainties, the numbers are staggering. We are surrounded by more stars than we could ever count, more than we could ever visit, more than we could ever name. And each one is a sun. Each one could have planets. Each one is a nuclear furnace, fusing hydrogen into helium and releasing the energy that makes it shine. Let us think about that for a moment. Every point of light you see in the night sky is a star like our sun. Some are larger, some are smaller, but each one is undergoing the same basic process. Gravity pulls hydrogen gas together. The pressure at the core becomes so intense that hydrogen atoms fuse into helium. This fusion releases enormous amounts of energy, which pushes outward against gravity. The balance between gravity pulling in and fusion energy pushing out keeps the star stable for millions or billions of years. Eventually, the hydrogen in the core runs out. The star's fate then depends on its mass. A star like our Sun will swell into a red giant, then shed its outer layers and leave behind a dense remnant called a white dwarf. A more massive star will end its life in a supernova explosion, its core collapsing into a neutron star or even a black hole. These stellar deaths are not endings so much as transformations. The elements forged in stellar cores are scattered into space by stellar winds and supernova explosions. These elements, carbon, oxygen, nitrogen, iron, become the raw materials for new stars, new planets, new life. Every atom in your body was forged in the heart of a star. You are literally made of stardust. This is one of the most profound discoveries of modern astronomy, the connection between stars and life. The universe is not just a collection of distant lights. It is a vast chemical factory, producing the elements that make planets, oceans, atmospheres, and organisms. When we count the stars, we are in a sense counting the forges where the building blocks of life are made. And there are so many of them. 100 sextillion stellar forges, each one burning for millions or billions of years, each one contributing to the cosmic inventory of elements. Over the life of the universe, stars have converted about 2% of all hydrogen into heavier elements. It does not sound like much, but it is enough. It is enough for planets, enough for water, enough for us. Let us take a moment to appreciate the sheer improbability of our existence. Of all the places you could be in the universe, you are here, on this small planet, orbiting this ordinary star, in this vast galaxy. The odds of being anywhere in particular are impossibly small. And yet, here you are, listening to these words, thinking about the stars. The universe does not care about odds or probabilities. It simply is. The stars simply shine, and we simply exist for this brief moment, aware of the cosmos that surrounds us. There is something beautiful in that, something peaceful. The universe asks nothing of us. It simply offers itself for contemplation. Now, let us push our inquiry to its limits. We have talked about the observable universe, the region from which light has had time to reach us. We have estimated that this region contains around 200 sextillion stars. But what about the universe beyond? The observable universe has a boundary, the cosmic horizon. Beyond this boundary, light has not had time to reach us. The universe could extend billions or trillions of light years beyond what we can see. Or it could be infinite. If the universe is infinite, then the number of stars is also infinite. Every finite number becomes meaningless in the face of infinity. There would be not just sextillions of stars, but an endless count, a number that continues forever without bound. Some cosmological models suggest the universe might be finite but unbounded. Imagine the surface of a sphere. If you walk in one direction on a sphere's surface, you never reach an edge. You just keep going around and around. The universe could be like that, a three-dimensional version of a sphere's surface, finite in volume but without boundaries. In such a universe, there would be a very large but finite number of stars. Other models suggest the universe is truly infinite. In this case, the number of stars is infinite, and no counting can ever capture the total. An infinite universe would contain infinite copies of everything, including infinite copies of you reading infinite copies of these words. The implications are mind-bending. We do not know which model is correct. We may never know. The universe beyond the cosmic horizon is forever hidden from us. We can speculate, we can model, we can theorize, but we cannot observe. What we can say is that the observable universe alone contains more stars than we can comprehend, and that number grows as our telescopes improve. Each new observation reveals galaxies we missed before, stars we could not see. The James Webb Space Telescope is already finding galaxies at greater distances than Hubble could reach. In the coming years, our estimates will be refined. The number may go up, the number may go down, but it will remain staggeringly, incomprehensibly large. So what is the answer to our original question? How many stars are in the universe? For the observable universe, our best estimate is around 10 to the 23rd. That is 100 to 200 sextillion stars, a number so large that it has no meaning in everyday terms. A number that can only be felt through analogies and comparisons. More stars than grains of sand on all the beaches of Earth. More stars than seconds since the Big Bang. More stars than words ever spoken by every human who ever lived. The universe is generous with stars. It has scattered them in such abundance that scarcity is inconceivable. And yet, for all this abundance, the universe is mostly empty. The space between stars is vast beyond measure. If you shrunk the sun down to the size of a grain of sand, the nearest star, Proxima Centauri, would be another grain of sand about 4 miles away. The space in between would be empty, just void, just vacuum. This emptiness is part of what makes the universe so strange and beautiful. Matter is rare. Stars are rare. And yet there are so many of them because space is so impossibly large. The universe is like an ocean where every drop of water is separated by miles of emptiness. And yet, there are still enough drops to fill all the oceans of Earth and more. Let us continue our exploration by considering some of the individual stars that contribute to this vast count. Our own Sun is one of them. It is a yellow dwarf, about 4.5 billion years old, roughly middle-aged for a star of its type. It will continue burning hydrogen for another 5 billion years or so, then expand into a red giant and eventually fade into a white dwarf. From the perspective of the universe, our Sun is utterly ordinary. There is nothing special about it. And yet, from our perspective, it is everything. It provides the energy that makes life on Earth possible. The nearest star to our Sun is Proxima Centauri, a tiny red dwarf about 4.2 light-years away. Proxima is so dim that it cannot be seen with the naked eye, even though it is the closest star in the cosmos to us. It has at least 2 planets, one of which orbits in the habitable zone where liquid water could exist. Whether life has ever arisen, there is a question we cannot yet answer. Proxima Centauri is part of a triple star system. It orbits at a great distance from 2 other stars, Alpha Centauri A and Alpha Centauri B. These 2 stars are similar in size to our Sun and orbit each other every 80 years or so. Proxima takes hundreds of thousands of years to complete one orbit around them. The Alpha Centauri system is visible to the naked eye from the southern hemisphere, appearing as a single bright point of light. The brightest star in our night sky is Sirius, the dog star. It lies about 8.6 light-years away and shines with a blue-white light. Sirius is actually a binary star system. The primary star, Sirius A, is about twice as massive as our Sun and 25 times more luminous. Its companion, Sirius B, is a white dwarf, the dense remnant of a star that exhausted its fuel long ago. Sirius B is about the size of Earth, but contains almost as much mass as our Sun. Moving farther out, we encounter some of the most extreme stars in our galaxy. Betelgeuse, in the constellation Orion, is a red supergiant near the end of its life. It is so large that if it replaced our Sun, its surface would extend beyond the orbit of Mars. Betelgeuse will eventually explode as a supernova, perhaps within the next 100,000 years. When it does, it will be visible in daylight and will outshine the full moon at night. For a brief moment, one of our galaxy's stars will blaze across the sky before fading forever. At the other extreme is the star called R136A1, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. R136A1 is one of the most massive stars known, with a mass over 200 times that of our Sun. It is also one of the most luminous, shining with the light of nearly 9 million suns. Such massive stars are rare and short-lived. R136A1 is only a few million years old, but is already approaching the end of its life. It will explode as a supernova, or perhaps collapse directly into a black hole. Between these extremes lies the vast majority of stars. Red dwarfs that burn slowly for trillions of years. Yellow dwarfs like our Sun that provide stable light for billions of years. Orange dwarfs slightly smaller and cooler than the Sun. Blue stars that burn hot and fast. White dwarfs that cool slowly over billions of years. Neutron stars that spin rapidly and emit beams of radiation. And black holes, the dark remnants of the most massive stars, from which not even light can escape. Each of these objects contributes to our count of stars. Depending on how you define a star, the total may vary. Some astronomers count only objects currently undergoing nuclear fusion in their cores. Others include stellar remnants like white dwarfs and neutron stars. Black holes are typically not counted as stars, even though they formed from stars. Brown dwarfs, objects too small to sustain hydrogen fusion, occupy a grey zone between stars and planets. The distinctions matter for precise counting, but do not change the overall picture. The universe contains an almost unimaginable number of star-like objects, whether they are actively fusing hydrogen or have long since stopped. The light we see from distant galaxies comes from all these sources combined. Speaking of light, let us consider what happens to all the light produced by all these stars. Every second, the stars of the universe emit photons in numbers that rival the stars themselves. These photons travel through space, crossing billions of light years, illuminating the cosmos. Some reach our telescopes and allow us to see distant galaxies. Some are absorbed by dust and re-emitted as infrared light. Some travel forever through expanding space, never striking anything. The total light output of all the stars in the observable universe creates what is called the extragalactic background light. This is a faint glow that fills all of space, made up of photons that have been traveling since the universe was young. By measuring this background light, astronomers can estimate how much light all the stars have ever produced. This in turn helps refine estimates of how many stars exist and how long they have been shining. The extragalactic background light tells us that stars have been producing energy throughout cosmic history. The first stars formed a few 100 million years after the Big Bang. Since then, stars have been forming and dying in an ongoing cycle. The total energy released by all these stars is immense, enough to fill all of space with a faint glow that our instruments can detect. Now let us explore the connection between stars and the planets that orbit them. For centuries, astronomers wondered whether other stars had planets. Our solar system seemed to suggest that planets were a natural byproduct of star formation. But proving this was difficult. Planets are tiny compared to stars and produce no light of their own. They are lost in the glare of their parent stars. The first definitive detection of a planet around another star came in 1995. Astronomers Michel Mayor and Didier Queloz discovered a planet orbiting the star 51 Pegasi. about 50 light-years from Earth. This planet, called 51 Pegasi b, was unlike anything in our solar system. It was a gas giant, similar in size to Jupiter, but orbiting so close to its star that its year lasted only 4 days. Such planets, called hot Jupiters, were a surprise. They suggested that planetary systems could be very different from our own. Since then, astronomers have discovered thousands of exoplanets. The Kepler Space Telescope, launched in 2009, revolutionized the field. Kepler monitored over 150,000 stars, watching for the tiny dimming that occurs when a planet passes in front of its star. By 2018, Kepler had discovered over 2,600 confirmed exoplanets, with thousands more candidates awaiting confirmation. The Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, continues this work. TESS is surveying the entire sky, looking for planets around the nearest and brightest stars. Ground-based telescopes contribute as well, using techniques like radial velocity measurements and direct imaging to find planets. What have we learned? We have learned that planets are common, very common. Statistical analyses of Kepler data suggest that most stars have at least one planet. Some estimates indicate that there may be more planets in the galaxy than stars. If the Milky Way contains 200 billion stars, it may contain over 300 billion planets. Extrapolating to the observable universe, with its 2 trillion galaxies and 200 sextillion stars, the number of planets becomes even more staggering. There could be over 1 trillion planets in the observable universe. That is a 1 followed by 24 zeros. Each one is a world. Each one has its own geology, its own chemistry, its own history. Some may harbor life. This brings us to one of the deepest questions humanity has ever asked. Are we alone? In a universe with so many stars and so many planets, is Earth the only place where life has arisen? Or is life common, scattered across the cosmos like the stars themselves? We do not yet know the answer. We have searched for signals from extraterrestrial civilizations and found none. We have looked for signs of life in our own solar system, on Mars, on the moons of Jupiter and Saturn, and found no definitive evidence. Life may be rare. It may require conditions so specific that Earth is truly unique. Or life may be common, but separated by such vast distances that contact is impossible. A civilization in the Andromeda Galaxy could be broadcasting signals right now, but those signals would take over 2 million years to reach us. We would never know they existed until long after both civilizations had faded. The question of life is intimately connected to the question of stars. Stars provide the energy that life needs. They forge the heavy elements that make up planets and organisms. They determine the conditions on the planets that orbit them. Without stars, there would be no chemistry, no geology, no biology. Just cold, dark, empty space. So when we count the stars, we are in a sense counting the possibilities for life. Each star is a potential home for worlds. Each world is a potential home for life. The universe is not just vast in terms of space. It is vast in terms of potential. Now let us return to the beginning. The question was simple. How many stars are in the universe? The answer, as we have seen, is not so simple. It depends on how you count, what you count, and how far you extend your count. For the observable universe, the part we can see, the estimate is around 10 to the 23rd stars. That is 1 followed by 23 zeros. Or written another way, about 1 to 200 sextillion stars. This number includes all the stars in all the galaxies that light has had time to reach from since the Big Bang. for the universe beyond the observable, we cannot say. It might be finite, containing some larger but still countable number. It might be infinite, containing an endless number of stars that no count could ever capture. We simply do not know. What we do know is that the observable universe alone contains more stars than any human could ever contemplate. More stars than grains of sand. More stars than words ever spoken. More stars than drops of water in all the oceans. More stars than almost anything you could choose for comparison. And all of these stars are suns. They burn with nuclear fire. They emit light and heat. They illuminate the darkness of space. They forge the elements of chemistry. They provide the energy for life. Each one is a beacon in the void. Let us take a moment to appreciate the beauty of this. The night sky, which seems so peaceful and still, is actually filled with violence and energy. Every point of light is a thermonuclear furnace, converting mass into energy through processes that human engineers can only dream of replicating. The stars are fierce and powerful beyond measure. And yet, from our vantage point on Earth, they appear as gentle twinkling points of light. They fill us with wonder rather than fear. This is one of the great gifts of distance. The universe is dangerous. Stars explode. Black holes devour. Radiation floods through space. And yet, we are safe here, on our small planet, warmed by our modest star. The dangers are so far away that they become beautiful. The violence becomes poetry. Perhaps this is why humans have always been drawn to the stars. They are far enough away to be safe but close enough to be seen. They invite contemplation without demanding action. They are the perfect objects for wonder. And wonder is what we feel when we consider the number of stars. Wonder at the scale. Wonder at the beauty. Wonder at the fact that we exist at all, here in this vast cosmos, able to ask questions and seek answers. The universe does not owe us understanding. It does not owe us anything. And yet, it allows us to look and to learn. That is a kind of gift. Let us explore some more of the wonders that our star counting has revealed. Consider the life cycle of a star. A star is born when a cloud of gas and dust collapses under its own gravity. The collapse causes the center of the cloud to heat up. Eventually, the temperature and pressure become so great that hydrogen atoms begin to fuse into helium. This fusion releases energy, and a star is born. The star will spend most of its life in a stable phase, fusing hydrogen in its core. Our Sun has been doing this for about 4.5 billion years and will continue for another 5 billion. During this time, the star maintains a balance between the inward pull of gravity and the outward push of energy from fusion. Eventually, the hydrogen in the core runs out. What happens next depends on the star's mass. A low-mass star, like a red dwarf, simply fades away over trillions of years. A medium-mass star, like our Sun, expands into a red giant as it begins fusing helium in its core. The red giant phase lasts only a few 100 million years. Then the star sheds its outer layers, creating a beautiful planetary nebula. The core remains as a white dwarf, a dense ball of carbon and oxygen that slowly cools over billions of years. A high-mass star has a more dramatic end. After exhausting its hydrogen, it fuses heavier and heavier elements. Helium becomes carbon, carbon becomes neon, neon becomes oxygen, oxygen becomes silicon, silicon becomes iron. But iron is the end of the line. Fusing iron absorbs energy rather than releasing it. When the core fills with iron, fusion stops, and the core collapses in a fraction of a second. The collapse triggers a supernova, one of the most energetic events in the universe. The outer layers of the star are blasted into space at thousands of kilometers per second. For a brief time, the supernova outshines entire galaxies. The core is crushed into a neutron star, a ball of neutrons about 20 kilometers across, with a mass greater than the Sun's. If the star was massive enough, the core collapses all the way into a black hole. These stellar deaths are crucial for the chemistry of the universe. During a star's life, it fuses light elements into heavier ones, but many of the heaviest elements, like gold and platinum, are not made inside stars. They are made in the extreme conditions of supernova explosions and neutron star collisions. When a star explodes, it spreads these elements into space. They become part of the gas clouds that will form the next generation of stars and planets. This is called nucleosynthesis, and it has been going on since the first stars formed. Each generation of stars enriches the universe with heavier elements. The first stars, formed from nearly pure hydrogen and helium, were very different from stars today. They may have been much more massive and burned out quickly. Their supernovae seeded the universe with the first heavy elements, allowing the next generation of stars to form planets with metals and minerals. Our Sun is at least a third-generation star. The elements in our solar system were made by multiple generations of stars that lived and died before our Sun was born. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in ancient stars. You are connected to the cosmos in the most intimate way possible. You are made of stars. This connection becomes even more profound when we consider the numbers. Every one of those 100 sextillion stars is going through its own life cycle. Some are being born right now, collapsing from gas clouds in stellar nurseries. Some are in their middle age, burning steadily like our Sun. Some are dying, expanding into giants, shedding their layers, exploding as supernovae. And some are already dead, cooling as white dwarfs, spinning as neutron stars, lurking as black holes. The universe is in constant flux. Stars are not static points of light. They are dynamic objects, changing over time, interacting with their environments, influencing the galaxies around them. The star count we have discussed is a snapshot, a picture of the universe at one moment. In the past, the number was different. In the future, it will be different again. Looking back in time, we see that the rate of star formation has changed over cosmic history. The universe went through a peak of star formation about 10 billion years ago. During this era, stars were forming at a rate many times higher than today. Galaxies were young and gas-rich. They had the raw materials needed to form new stars. Since then, the rate of star formation has declined. Galaxies have used up much of their gas. The remaining gas is often too hot or too diffuse to collapse into stars. In the Milky Way today, only a few new stars form each year. This is a far cry from the frenzied star formation of the early universe. Looking forward, we can predict what will happen. As galaxies continue to form stars, they will gradually exhaust their gas reserves. Star formation will slow and eventually cease. The last stars will be low-mass red dwarfs, which burn their fuel so slowly that they can shine for trillions of years. But eventually, even they will run out of fuel. In the very far future, perhaps 100 trillion years from now, the last stars will fade away. The universe will enter a dark era. No new stars will form. The only light will come from cooling white dwarfs and the occasional collision of stellar remnants. Eventually, even these sources will go dark. But this is not something to mourn. It is simply the nature of things. The universe had a beginning, and it will have an end. at least in terms of stars. But the atoms that make up the stars will still exist. They will drift through space for eternity, perhaps coming together again in some far future we cannot imagine. The universe has a way of recycling itself. For now, though, the stars shine. The universe is young. We are living in the stellar era, when the cosmos is lit by the fires of fusion. This era will last for billions of years yet. We have time. Time to wonder. Time to explore. Time to count the stars and marvel at their number. Let us return to the comparison that started our journey. Stars and sand. There are more stars in the universe than grains of sand on Earth. This simple statement contains within it a profound truth about the scale of the cosmos. Scientists have estimated that there are roughly 7.5 times 10 to the 18th grains of sand on Earth. That is 7.5 quintillion grains. This number comes from estimating the volume of all beaches, deserts, and sandy areas on the planet, and dividing by the volume of an average grain of sand. The number of stars in the observable universe is around 10 to the 23rd. Divide the second number by the first, and you get about 30,000. For every grain of sand on Earth, there are 30,000 stars in the observable universe. If you went to a beach and picked up a single grain of sand, you would need to imagine 30,000 stars for just that one grain. Try this the next time you visit a beach. Hold up a single grain of sand against the night sky. Each of those tiny points of light you see represents perhaps 1 million grains of sand worth of stars in the wider universe. The grain in your hand is connected to all of them. The same elements, forged in stars, make up both the sand and the stars. Or consider another comparison. How long would it take to count all the stars? Let us assume you count at a rate of 1 star per second. That is pretty fast. Try counting out loud at that pace for a minute. You will reach 60. Now imagine doing that without stopping. No breaks, no sleep, just counting. 1 number per second for the rest of your life. If you lived for 100 years and counted every second, you would count about 3.2 billion stars. That is a lot, but it is less than 1% of the stars in our own galaxy. To count all the stars in just the Milky Way at 1 per second would take over 10,000 years. No human lifespan could accomplish it, and the Milky Way is just one galaxy. To count all the stars in the observable universe at 1 per second would take about 3 times 10 to the 15th years. That is 3 quadrillion years. The universe is only about 14 billion years old. You would need to count for over 200 million times longer than the universe has existed. These comparisons help us grasp the impossibility of the number. We cannot count the stars. We cannot visit them. We cannot name them. They are simply too numerous. The best we can do is estimate, and even our estimates are rough approximations. But there is something freeing in this impossibility. We do not need to count every star to appreciate them. We do not need to visit every galaxy to understand the universe. The sheer abundance of stars tells us something profound about the nature of existence. The universe is generous. It does not hoard its wonders. It scatters them lavishly across space and time. Let us think about what it means for there to be so many stars. Each star has its own story, each one formed in its own way, from its own gas cloud, at its own time. Each one has its own set of planets, or lack thereof. Each one burns with its own color and brightness. Each one will die its own death. The diversity is staggering. No 2 stars are exactly alike. Even stars of the same type differ in age, composition, and circumstances. The star we call the Sun has unique characteristics that distinguish it from every other star in the universe. It is ours. It is home. And yet, The Sun is ordinary. It is a common type of star. There are billions of stars very similar to it in our galaxy alone. This ordinariness is itself extraordinary. It suggests that the conditions for forming sun-like stars are common in the universe. It suggests that planets like Earth might be common too. The search for other Earths is one of the great scientific endeavors of our time. Astronomers are using every tool at their disposal to find planets similar to our own. Rocky planets, planets with liquid water, planets in the habitable zone of their star. Each discovery brings us closer to answering the question of whether we are alone. The numbers are encouraging. Based on Kepler data, astronomers estimate that there may be billions of Earth-like planets in the Milky Way. If even a small fraction of these have the right conditions for life, the number of potential homes for life in just our galaxy could be in the millions. Extend this to the observable universe with its trillions of galaxies, and the number becomes astronomical in the truest sense. Of course, we do not know if life arises easily or with difficulty. We have only one example of life emerging here on Earth. We do not know how improbable that event was. Life could be common, arising wherever conditions permit. Or life could be rare, requiring such a specific set of circumstances that it has happened only once. This is the great unknown, and it is connected directly to the stars. The stars provide the energy for life. The stars create the elements of life. The stars host the planets where life might exist. Understanding the stars is, in a deep sense, understanding ourselves. So let us celebrate the stars. Let us marvel at their number. Let us appreciate the light that travels across billions of years to reach our eyes. Let us remember that each point of light is a sun, with its own story, its own planets, its own possibilities. The universe is vast beyond comprehension, and it is filled with fire. Now let us explore some of the stranger stars that populate our universe. Not all stars are simple spheres of burning gas. Some have evolved into exotic forms that push the boundaries of physics. Understanding these extreme objects helps us appreciate the full range of what counts as a star. White dwarfs are the first type of stellar remnant we encounter. When a medium-mass star exhausts its nuclear fuel, it sheds its outer layers and leaves behind a dense core. This core is a white dwarf. It is no longer fusing elements. It shines only because it is still hot from its past activity. Over billions of years, a white dwarf slowly cools, eventually becoming a cold, dark black dwarf. But the universe is not old enough for any black dwarfs to exist yet. White dwarfs are incredibly dense. A typical white dwarf contains about half the mass of our Sun, compressed into a sphere the size of Earth. A teaspoon of white dwarf material would weigh several tons on Earth. This extreme density is supported by a quantum mechanical effect called electron degeneracy pressure. The electrons in the white dwarf resist being squeezed together, and this resistance holds the star up against gravity. There is a limit to how massive a white dwarf can be. Above about 1.4 times the mass of the Sun, electron degeneracy pressure cannot hold the star up. This limit is called the Chandrasekhar limit, named after the physicist who discovered it. If a white dwarf somehow gains enough mass to exceed this limit, it will collapse further, triggering a type Ia supernova. Neutron stars are even more extreme. They form when a massive star explodes as a supernova, and its core collapses beyond the white dwarf stage. The electrons and protons are crushed together to form neutrons. The result is a ball of neutrons about 20 kilometers across, containing more mass than the Sun. A neutron star is so dense that a teaspoon of its material would weigh about 1 billion tons. The surface gravity is so strong that if you could somehow stand on a neutron star, you would be flattened to a layer of atoms in an instant. The escape velocity from a neutron star is about half the speed of light. Light itself is significantly bent as it passes near the surface. Neutron stars spin rapidly. When they first form, they may rotate hundreds of times per second. This rapid rotation, combined with their strong magnetic fields, produces beams of radiation that sweep through space like lighthouse beams. If one of these beams happens to point toward Earth, we see a regular pulse of radiation. Such neutron stars are called pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. The regular pulses were so precise that the discoverers briefly wondered if they might be signals from an extraterrestrial civilization. They jokingly called the source LGM-1 for Little Green Men. It was soon recognized as a natural phenomenon, but the precision of pulsar timing remains astonishing. Some pulsars keep time better than atomic clocks. Neutron stars can also be part of binary systems. When a neutron star has a companion star, it can pull material from that companion. This material spirals down onto the neutron star, releasing tremendous amounts of X-ray radiation. These systems are called X-ray binaries, and they are among the brightest X-ray sources in the sky. In some cases, two neutron stars orbit each other. Over millions of years, they spiral inward, losing energy to gravitational waves. Eventually, they collide and merge. Such a collision was detected for the first time in 2017, when the gravitational wave observatories LIGO and Virgo detected the merger of two neutron stars. This event, called GW170817, was also seen in light, from gamma rays to radio waves. It confirmed that neutron star mergers produce heavy elements like gold and platinum. Beyond neutron stars lie black holes. A black hole forms when the core of a very massive star collapses beyond even the neutron star stage. The gravity becomes so strong that not even light can escape. The boundary of no return is called the event horizon. Once anything crosses the event horizon, it is lost to the outside universe forever. Black holes are strange objects. They are defined not by their material but by their gravity. From the outside, a black hole is characterized by just three properties: its mass, its spin, and its electric charge. Everything else about the matter that fell into the black hole is lost. This is sometimes called the no-hair theorem. Black holes have no hair, meaning no distinguishing features beyond these three numbers. Despite their name, black holes are not truly invisible. Matter falling toward a black hole forms a swirling disk of superheated gas called an accretion disk. This disk glows with intense radiation, making the region around the black hole one of the most energetic environments in the universe. The first image of a black hole's shadow, surrounded by its glowing accretion disk, was captured in 2019 by the Event Horizon Telescope. Black holes come in different sizes. Stellar mass black holes form from the deaths of massive stars. They typically contain 5 to 50 times the mass of our Sun. Intermediate mass black holes, if they exist, would contain hundreds to thousands of solar masses. Their existence is still debated. At the extreme end are supermassive black holes. These contain millions to billions of times the mass of our Sun. They lurk at the centers of most large galaxies, including our own Milky Way. The supermassive black hole at the center of our galaxy is called Sagittarius A star. It contains about 4 million solar masses and is located about 26,000 light-years from Earth. Supermassive black holes power some of the most luminous objects in the universe. when a supermassive black hole is actively feeding, it can outshine an entire galaxy. These objects are called active galactic nuclei, or quasars when they are particularly bright. The most distant quasars we have observed shine so brightly that we can see them from over 13 billion light-years away. They existed when the universe was less than 1 billion years old. The existence of supermassive black holes in the early universe is a puzzle. How did they grow so large so fast? One possibility is that they formed from the direct collapse of massive gas clouds, skipping the stellar phase entirely. Another is that they formed from the mergers of many smaller black holes. The answer is still unknown. These exotic objects, white dwarfs, neutron stars, and black holes, are the endpoints of stellar evolution. They are what remains when stars die. Though they no longer shine from fusion, they are still counted as part of the stellar census. The universe contains billions of these remnants, scattered through galaxies like bones of ancient giants. Now let us turn our attention to the youngest members of the stellar population. Stars are being born even as you listen to these words. In vast clouds of gas and dust scattered throughout galaxies, gravity is pulling matter together, starting the process that will eventually create new suns. These stellar nurseries are some of the most beautiful objects in the cosmos. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, is one of the nearest star-forming regions. Within it, hundreds of young stars are emerging from their cocoons of gas. The nebula glows with the light of these young stars, its colors created by the fluorescence of hydrogen and other gases. The process of star formation begins with a molecular cloud, a vast, cold region of space filled with hydrogen molecules and dust. These clouds can be dozens or hundreds of light-years across. They are not uniform. Denser regions within the cloud slowly contract under their own gravity. As the density increases, the contraction accelerates. Eventually, a dense core forms, surrounded by a rotating disk of gas and dust. The core continues to collapse, heating up as gravitational energy is converted to thermal energy. When the center reaches about 10 million degrees, hydrogen fusion begins, and a star is born. The remaining disk may eventually form planets, as material clumps together and grows through collisions. The timescale for this process depends on the mass of the forming star. Massive stars form quickly, in just a few 100,000 years. They burn through their fuel just as quickly, living for only a few million years. Low-mass stars form more slowly, taking millions of years to complete the process. But once they ignite, they can burn for trillions of years. Star formation does not happen one star at a time. Stars typically form in groups, called stellar associations or open clusters. The Pleiades, a beautiful star cluster visible to the naked eye in the constellation Taurus, is an example of a young open cluster. Its stars formed together about 100 million years ago and are still relatively close to each other. Over time, the stars in an open cluster drift apart, dispersing into the general population of the galaxy. The rate of star formation varies across the universe. In some galaxies, called starburst galaxies, stars are forming at a prodigious rate. These galaxies may be undergoing mergers with other galaxies, which compresses the gas and triggers rapid star formation. The galaxy M82, the Cigar Galaxy, is a famous example. It is forming stars at a rate about 10 times higher than the Milky Way. Other galaxies have very little star formation. Elliptical galaxies, which are dominated by old red stars, have largely stopped forming new stars. They have used up or lost their gas reserves. The stars in elliptical galaxies are typically billions of years old, and few new stars are being added. The Milky Way is somewhere in between. It is a spiral galaxy with ongoing star formation in its spiral arms, where gas is compressed by density waves. The rate of star formation in our galaxy is about 1 to 3 solar masses per year. That is enough material to make 1 or 2 sun-like stars, or several smaller stars, or occasionally a portion of a more massive star. When we count the stars in the universe, we are counting stars at all stages of this process. Some are just forming, still hidden within their birth clouds. Some are in the prime of life, steadily fusing hydrogen. Some are aging, expanding into giants or shedding their layers. And some are already dead, cooling as white dwarfs or lurking as black holes. The diversity of stellar ages contributes to the diversity of stellar properties. A population of stars with mixed ages will have a range of temperatures, luminosities, and colors. By studying the distribution of these properties, astronomers can learn about the history of star formation in a galaxy. This is called stellar archaeology. The stars are the fossils that record the history of the cosmos. One remarkable discovery of stellar archaeology is that the first stars were very different from the stars we see today. The early universe contained only hydrogen, helium, and trace amounts of lithium. The first stars, called population 3 stars, formed from this pristine material. Without heavier elements to help cool the gas, these clouds could only collapse if they were very massive. As a result, population 3 stars may have been giants, hundreds of times more massive than the Sun. These first stars lived fast and died young. After just a few million years, they exploded as supernovae, scattering the first heavy elements into space. These elements, carbon, oxygen, and others, mixed with the surrounding gas and enabled the formation of the next generation of stars. Population 2 stars contain small amounts of heavy elements. Population Semi stars, like our Sun, contain larger amounts. No population 3 stars have ever been observed directly. They burned out billions of years ago, but astronomers search for their signatures in the oldest stars that still exist, looking for chemical patterns that reveal the nature of the first stellar generation. Each discovery adds to our understanding of the universe's infancy. The stars we count today are the descendants of those first stars. They carry the legacy of billions of years of stellar evolution. The heavy elements in our Sun and in our bodies were forged by countless generations of stars that came before. We are the latest chapter in a story that began with the first starlight. This story continues. The universe will go on forming stars for billions of years yet. Each new star adds to the count. Each new star offers new possibilities for planets, for chemistry, for life. The number we have estimated, 100 sextillion stars, is not a final count. It is a snapshot of a dynamic, evolving cosmos. And that cosmos is stranger and more wonderful than we can fully comprehend. We have talked about normal stars, giant stars, dwarf stars, dead stars. But there are phenomena in the universe that stretch the concept of a star to its limits. Consider magnetas, a type of neutron star with an extremely powerful magnetic field. The magnetic field of a magneta is a quadrillion times stronger than Earth's magnetic field. It is so intense that it would be lethal from 1,000 kilometers away. The field twists and stresses the crust of the neutron star, causing occasional starquakes that release tremendous bursts of energy. Or consider strange stars, hypothetical objects made of strange matter rather than ordinary nuclear matter. Strange matter is a form of matter made of up, down, and strange quarks in roughly equal numbers. If strange matter is more stable than ordinary matter, then neutron stars might convert to strange stars over time. No strange stars have been definitively detected, but the possibility remains. At the boundaries of our knowledge, we find more questions than answers. The universe always has more to reveal. Every advance in our understanding opens new mysteries. This is the nature of science. This is the nature of exploration. We count the stars, and in doing so, we discover how much we still do not know. But perhaps the most profound mystery is the simplest. Why are there any stars at all? Why is the universe constructed in such a way that stars form, burn, and seed the cosmos with the elements of chemistry and life? The answer lies in the fundamental constants of nature, the strength of gravity, the charge of the electron, the mass of the proton. These numbers and dozens of others determine how the universe behaves. If any of them were slightly different, stars might not exist. Consider gravity. If gravity were slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang, before any stars could form. If gravity were slightly weaker, matter would never have clumped together into galaxies and stars. The universe would be a diffuse cloud of gas, eternal and empty. Or consider the strong nuclear force, which holds protons and neutrons together in atomic nuclei. If this force was slightly weaker, protons could not stick together, and there would be no atoms heavier than hydrogen, no helium, no carbon, no elements of life. If the force was slightly stronger, all the hydrogen in the early universe would have fused into helium, leaving no fuel for the stars we see today. These and other apparent fine-tunings have led some to wonder if the universe was designed for life. Others point to the possibility of a multiverse, where many universes exist with different constants. In most of these universes, stars do not form and life cannot arise. But in a few, like ours, the constants happen to allow stars, planets, and observers who can wonder about it all. We do not know which explanation is correct. We may never know. But what we do know is that the universe we inhabit is one where stars are possible. More than possible, they are abundant. The cosmos is filled with them, and their existence makes our existence possible. This is the deep connection between stars and life. Without stars, there would be no heavy elements. Without heavy elements, there would be no planets, no water, no organic chemistry. Without organic chemistry, there would be no life. The stars are not just beautiful lights in the sky. They are the engines that drive the chemistry of the cosmos. They are the furnaces where the building blocks of life are forged. Every carbon atom in your body was once inside a star. It was fused from helium in the core of a star that lived and died billions of years ago. The oxygen you breathe, the nitrogen in your proteins, the iron in your blood, all of it came from stars. You are a child of the stars. You are made of their remains. This is not a metaphor. It is literal scientific truth. The atoms of your body are recycled stardust. When you look up at the night sky, you are looking at your ancestors. Not your biological ancestors, of course, but your atomic ancestors. The stars that made the stuff of which you are made. There is something deeply comforting in this connection. We are not separate from the cosmos. We are part of it. The same processes that shaped the stars shaped us. The same elements that burn in distant suns flow in our veins. We belong to the universe in the most intimate way. And the universe is vast. It contains more stars than we can count, more galaxies than we can explore, more wonders than we can imagine. This vastness could feel lonely. It could make us feel small and insignificant, but it does not have to. Instead, it can make us feel connected to something immense and beautiful. Consider what it means to be alive in such a universe. You are a collection of atoms that have come together in just the right way to be aware. You can look up at the stars and understand, at least partially, what they are. You can count them, or try to. You can wonder about their planets, their possibilities, their mysteries. This ability to wonder is itself a kind of miracle. The universe has been around for nearly 14 billion years. For most of that time, there was no one to see it. Stars formed and exploded. Galaxies collided and merged. Black holes grew and consumed. And no one noticed. No one cared. The cosmos was a stage with no audience. Then life arose. Perhaps on Earth, perhaps elsewhere, perhaps in many places. Slowly, over billions of years, some of that life developed the ability to look out at the universe and ask questions. What are those lights in the sky? How far away are they? How many are there? We are the universe, becoming aware of itself. This is not just poetic language. It is a statement of fact. The atoms that make up your brain were once scattered across the cosmos, in gas clouds and dying stars. Now they have organized themselves in such a way that they can contemplate their own origins. The universe is looking at itself through your eyes. This perspective can transform how we see the night sky. Those points of light are not just distant objects. They are relatives, cousins. The same fundamental processes that created them created us. We share a common origin in the Big Bang, a common chemistry in stellar fusion, a common future in the long, slow cooling of the cosmos. So when we ask how many stars there are, we are asking about our family. How many cousins do we have? How many other suns? How many other worlds? How many other possibilities? The answer, 100 sextillion or more, tells us that we have a very large family indeed. Let us now begin to bring our journey to a close. We started with a simple question. How many stars are in the universe? We have traveled far to find the answer. From the dust clouds of the Milky Way to the most distant galaxies visible to our telescopes. From the birth of the first stars to the death of the last. From the subatomic realm of nuclear fusion to the cosmic web of galaxy clusters. The answer we have found is humbling. The observable universe contains approximately 10 to the 23rd stars. That is 100 to 200 sextillion stars, a number so large that it exceeds all comparisons to human experience. More than grains of sand, more than drops of water, more than seconds in the history of the universe. This number is an estimate, not an exact count. It is based on observations of galaxies, models of stellar populations, and extrapolations from what we can see to what we cannot. The true number might be larger or smaller, but the order of magnitude is likely correct. There really are that many stars. And this is only the observable universe. Beyond the cosmic horizon, there may be far more. If the universe is truly infinite, as some models suggest, then the number of stars is also infinite. No count could ever capture the total. The universe would simply go on forever, with stars beyond counting in every direction. But let us not lose ourselves in infinity. Let us return to what we can see, what we can know, what we can appreciate. The observable universe, with its 2 trillion galaxies and its sextillions of stars, is more than enough for a lifetime of wonder, more than enough for 1,000,000 lifetimes. Each of those stars has a story, each one formed in its own way, from its own cloud of gas, under its own circumstances. Each one has lived its own life burning hydrogen or helium or heavier elements. Each one will die its own death, fading or exploding or collapsing. The universe is a library of stellar biographies, and we have only begun to read them. Some of those stars have planets. Many of them, probably most. Planets of rock and planets of gas. Hot planets and cold planets. Planets with water and planets bone dry. Planets orbiting close to their stars and planets orbiting far away. The diversity of planets probably matches or exceeds the diversity of stars, and some of those planets, perhaps many, might harbor life. We do not know how common life is. We have only one example here on Earth, but the ingredients for life are common: carbon, oxygen, nitrogen, water. These are produced by stars and distributed throughout the universe. If life can arise from these ingredients, it may have arisen in countless places. This is the great question that follows from our count of stars. If there are so many stars and so many planets, is anyone else out there? Are we alone in the cosmos, or are we one of countless civilizations scattered among the stars? We do not know. We have searched for signals from extraterrestrial intelligences and found nothing convincing. We have looked for signs of life in our own solar system and found no evidence yet. The universe is silent as far as we can tell. Perhaps life is rare. Perhaps the conditions for life are so specific that they have occurred only on Earth. Perhaps we are the only minds in all the cosmos, the only observers in a universe of stars. Or perhaps life is common, but intelligence is rare. Perhaps countless planets are covered with microbes or plants or animals, but very few have developed the kind of intelligence that can build telescopes and ask questions about the stars. Or perhaps intelligent life is common, but separated by such vast distances that contact is impossible. The nearest star is over 4 light years away. The nearest intelligent civilization, if any exists, could be hundreds or thousands of light years away. Communication across such distances would take centuries or millennia. We cannot answer these questions yet, but we can wonder, and wondering is part of what makes us human. We look up at the stars and we imagine what might be out there. We count the stars and we imagine the possibilities that number represents. We dream of worlds beyond our own. The stars inspire us. They have inspired humans for as long as there have been humans. Ancient peoples told stories about the stars, seeing patterns and meanings in the random scattering of lights. They used the stars to navigate, to tell time, to mark the seasons. The stars were their companions and their guides. Modern humans still look to the stars for inspiration. We have sent probes to explore our solar system. We have sent humans to the moon. We dream of sending humans to Mars and beyond. The stars call to us, beckoning us to explore, to discover, to expand our horizons. And the sheer number of stars tells us that the horizon has no end. There will always be more to explore, more galaxies to observe, more stars to study, more planets to discover. The universe offers an endless frontier, a playground for the curious and the bold. This is perhaps the greatest gift of the stars, not just their light, not just their elements, but their invitation. They invite us to wonder, to question, to explore. They remind us that the universe is vast and full of mysteries. They challenge us to learn more, to go further, to never stop searching. So as you drift towards sleep tonight, carry with you the image of those sextillions of stars, each one a sun, each one a beacon in the darkness, each one a reminder that the universe is unimaginably large and yet somehow intimately connected to you. You are made of the same stuff as the stars. The atoms in your body were forged in stellar cores and scattered across space by stellar explosions. You are a child of the cosmos, a fragment of the universe that has awakened to contemplate itself. And in that contemplation, there is peace. The universe is not something to fear. It is something to marvel at. The vastness that could feel lonely instead feels like home. The billions of stars are your kin, your extended family, your ancestors and your descendants. Sleep now, knowing that you are part of something immense and ancient and beautiful. The stars shine on as they have for billions of years and will for billions more. They ask nothing of you but appreciation, and in return, they offer everything. Light, elements, wonder, a universe full of possibility. The journey we have taken tonight has been long, but we are not quite finished. There are a few more wonders to explore, a few more ideas to contemplate before we reach our final destination. Let us think about the future. Not your future or my future, but the future of the stars themselves. What will happen to all those sextillions of stars over the eons to come? In the short term, meaning the next few billion years, the universe will continue much as it is now. Stars will be born in molecular clouds. They will burn for millions or billions of years. They will die as white dwarfs, neutron stars, or black holes. New generations of stars will form from the remains of the old. Our own sun will evolve through its life cycle. In about 5 billion years, it will exhaust the hydrogen in its core and begin fusing helium. It will swell into a red giant, engulfing the orbit of Mercury and perhaps Venus. Earth will be scorched. The oceans will boil away. Life as we know it will end. Eventually, the sun will shed its outer layers, creating a planetary nebula. What remains will be a white dwarf, about the size of Earth, but containing half the sun's mass. This white dwarf will slowly cool over billions of years, eventually fading to a black dwarf, dark and cold. Similar fates await most of the stars in the universe. The majority of stars are red dwarfs, and they will burn for trillions of years. But even they will eventually exhaust their fuel. One by one, the stars will go out. The last stars to shine will be the smallest red dwarfs, those with masses just barely above the minimum needed for hydrogen fusion. They burn so slowly that they can shine for 10 trillion years or more. That is nearly 1,000 times the current age of the universe. But even they will eventually fade. When the last star goes out, the universe will enter a new era. Astronomers call it the degenerate era. The only stellar remnants will be white dwarfs, neutron stars, and black holes. White dwarfs will continue to cool, eventually becoming invisible black dwarfs. Neutron stars will spin down, their pulsar beams fading. Blacken. Holes will persist, slowly evaporating through a quantum process called Hawking radiation. This era will last for an almost inconceivable length of time. White dwarfs will take perhaps a quadrillion years to cool to near absolute zero. Black holes will take even longer to evaporate. The largest supermassive black holes might persist for 10 to the 100 years. That is a Google years. A number so large that writing it out would require more zeros than there are atoms in the observable universe. Eventually, even the black holes will be gone. The universe will enter its final era, sometimes called the dark era. There will be no sources of light, no sources of energy, just a thin scattering of particles drifting through an ever-expanding emptiness. This is the fate of the stars. This is the fate of the universe. It may seem bleak, but there is a kind of peace in it. The violence of stellar explosions will be over. The fury of black holes will have faded. The cosmos will be quiet at last. after trillions upon trillions of years of activity. And yet, this distant future is so far away that it has no bearing on our lives. The sun will shine for another 5 billion years. The stars will light the sky for trillions of years to come. We are living in the youth of the cosmos. The era of stars has barely begun. So let us not mourn a future that is unimaginably distant. Let us celebrate the present, when the stars blaze across the heavens, when new worlds are being discovered, when the universe is alive with light and possibility. Now let us return one more time to the number, 100 sextillion stars. What does this number really mean? Let us try a few more comparisons to help it sink in. Imagine that each star in the observable universe represented 1 second of time. 100 sextillion seconds is about 3 times 10 to the 15 years. That is 3 quadrillion years. The universe is about 14 billion years old. So the number of stars corresponds to a span of time more than 200,000 times longer than the age of the universe. Or imagine that each star represented 1 inch. 100 sextillion inches is about 2.5 times 10 to the 18th miles. The observable universe is about 93 billion light-years across, or about 5 times 10 to the 23 miles. So the number of stars, if laid out in inches, would stretch across a significant fraction of the observable universe. Or consider computer storage. If each star were a byte of data, you would have 100 zettabytes. The total amount of data created by humanity in the year 2020 was estimated at about 64 zettabytes. So the number of stars corresponds to roughly the amount of data humanity generates in a couple of years. Of course, we cannot actually store that much data yet, but the comparison gives a sense of scale. These comparisons are attempts to domesticate the number, to bring it within the range of human comprehension. They succeed only partially. 100 sextillion remains beyond our intuitive grasp. It is simply too large, but perhaps that is fitting. The universe is not built to human scale. It is built to cosmic scale, where distances are measured in light years and time is measured in billions of years. The number of stars reflects this scale. It is appropriate to the immensity of space and time, and there is beauty in immensity. The sheer scale of the universe inspires awe. It humbles us. It reminds us that we are small, but that we are also connected to something vast. We are part of the cosmos, and the cosmos is unimaginably large. Let us now consider one more aspect of the stars, their light. The light of a star is a message, traveling across space at 300,000 kilometers per second. When you see a star, you are receiving that message, photons that left the star years or centuries or millennia ago. The light from the sun takes about 8 minutes to reach Earth. The light from Proxima Centauri takes about 4 years. The light from Sirius takes about 8.5 years. The light from Betelgeuse takes about 700 years. The light from the most distant galaxies visible to Hubble has been traveling for over 13 billion years. This means that the universe is a time machine. When you look at the stars, you are looking into the past. You see them not as they are now, but as they were when their light began its journey. The farther you look, the further back in time you see. The most distant objects visible to our telescopes are so far away that their light has been traveling since shortly after the Big Bang. We see them as they were when the universe was young. Infant galaxies, still forming their first stars. Quasars powered by supermassive black holes feeding on primordial gas. A universe very different from the one we know today. And yet, we cannot see beyond a certain point. The cosmic microwave background, the faint glow left over from the early universe, marks the limit of our vision. before the universe was about 380,000 years old, it was opaque. Light could not travel freely, so we cannot see anything older than that. Beyond the cosmic microwave background lies the Dark Ages, a period when the universe was filled with neutral hydrogen, but no stars. We cannot observe this era directly. Then came the cosmic dawn, when the first stars ignited and began to light up the universe. Finding these first stars is one of the great goals of modern astronomy. The James Webb Space Telescope is designed to peer into this era. Its infrared vision can detect light that has been stretched by the expansion of the universe from visible to infrared wavelengths. Already, Webb has found galaxies at greater distances than ever before, pushing back our view toward the cosmic dawn. Each discovery refines our understanding of the universe. Each observation adds to our count of stars. The number we have discussed, 10 to the 23rd, is based on current knowledge. As our knowledge improves, the number may change, but the basic picture is likely to remain. The universe contains more stars than we can comprehend, more galaxies than we can visit, more wonders than we can fully appreciate, and that is enough. It is more than enough. A single star, with its nuclear fire and its planetary system, would be a wonder worthy of endless contemplation. A single galaxy, with its billions of stars, would be an ocean of discovery. The fact that there are trillions of galaxies, each with billions of stars, is almost too much abundance to process. Perhaps this is why we invented numbers, to help us deal with quantities beyond our immediate experience. Numbers allow us to talk about things we cannot directly perceive. We cannot see a sextillion stars, but we can write the number. We can calculate with it. We can compare it to other numbers and find meaning in the comparison. Numbers are a kind of magic. They let us grasp the ungraspable. They let us hold infinity in our minds, if only for a moment. The number 10 to the 23rd is just a symbol on a page or a sound in the air, but it points to something real. It points to all those stars burning in all those galaxies scattered across all of space. When you think about that number, you are thinking about something true. The universe really does contain that many stars. They really are out there shining, and you, thinking about them, are part of the same universe. You are connected to those stars by physics and chemistry and history. Let us hold this thought as we prepare to conclude our journey. The universe is vast, the stars are numerous, and we are here, aware of it all. The awareness itself is remarkable. For most of cosmic history, the universe went unseen. Stars burned and galaxies spun and no one noticed. Then, in a corner of one galaxy, on a small planet orbiting an ordinary star, something emerged that could notice. Life, consciousness, minds that could look up and wonder. We take this for granted, but we should not. The ability to wonder is not guaranteed by the laws of physics. It emerged through a long process of evolution, from the first self-replicating molecules to the complex brains of humans. It is a recent phenomenon in cosmic terms, appearing only in the last few 100,000 years of a 14 billion year history. And yet, here we are, wondering about the stars, counting them, marveling at their number. This is what the universe does when it reaches a certain level of complexity. It looks at itself and asks questions. You are the universe asking questions. Every thought you have about the stars is the cosmos contemplating itself. Every number you calculate is the universe doing mathematics. Every feeling of awe is the universe experiencing wonder. This is not mysticism. It is simple fact. You are made of atoms that were formed in stars, assembled by natural processes, organized by evolution into a pattern that thinks. When you think about the universe, you are the universe thinking about itself. And what thoughts they are. 100 sextillion stars, 2 trillion galaxies, 14 billion years of cosmic history. The scale is staggering, but the fact that we can even conceive of it is staggering too. A collection of atoms, pondering its own origins. A speck of matter, comprehending the immensity of space. This is the human condition. We are small, but we are aware. We are brief, but we can imagine eternity. We are limited, but we can conceive of infinity. The gap between our physical smallness and our mental reach is perhaps the most remarkable thing about us. The stars teach us this lesson every night. They are impossibly distant, impossibly numerous, impossibly ancient. And yet, we can see them. We can study them. We can count them. Our minds can span light years even though our bodies cannot. This is a kind of superpower. The ability to understand things far beyond our direct experience. No other species on Earth does this. No other species counts stars or ponders black holes or calculates the age of the universe. We are unique in this regard, at least on our planet. Perhaps there are other species elsewhere who do the same. Perhaps intelligent beings on planets around distant stars are looking out at the cosmos and counting the galaxies. Perhaps they have counted more accurately than we have. Perhaps they have found answers to questions we have not yet thought to ask. We do not know if such beings exist. The universe is silent as far as we can tell. But the sheer number of stars suggests that we might not be alone. If even a tiny fraction of those sextillion stars have planets, and a tiny fraction of those planets have life, and a tiny fraction of that life has evolved intelligence, there could still be millions or billions of intelligent species in the observable universe. Or there could be none but us. We are a sample size of one. We cannot calculate the odds. We can only wonder, and wondering is enough. The question itself is a gift. The ability to ask whether we are alone is a triumph of the human mind. It does not matter if we ever find the answer. The question connects us to the cosmos in a deep and meaningful way. So let us be grateful for the questions, grateful for the stars that inspire them, grateful for the minds that can ask them. We are small and brief and fragile, but we are also curious and courageous and capable of awe. The stars have been shining for billions of years, long before any human looked up to see them. They will continue shining for billions of years more, long after our species is gone. We are just a moment in the cosmic story. But what a moment it is. A moment when atoms became aware. A moment when matter looked up and saw the light of other suns. A moment when the universe, through us, began to understand itself. This understanding is fragile. It depends on the survival of our species, the continuation of our curiosity, the preservation of our knowledge. There is no guarantee that it will last. Civilizations rise and fall. Species evolve and go extinct. The universe does not owe us permanence. But for now, we are here. We are wondering. We are counting the stars. And that is something precious, something worth protecting, something worth celebrating. As we approach the end of our journey, let us gather together everything we have learned. Let us hold in our minds the full picture of the cosmic census we have attempted. We began with our own galaxy, the Milky Way, a barred spiral galaxy, about 100,000 light-years across, containing between 100 billion and 400 billion stars. Our Sun is one of those stars, located about 2/3 of the way out from the center, in one of the spiral arms. We are not special. We are simply one star among hundreds of billions. From there, we looked outward, We discovered that the Milky Way is just one galaxy among trillions. The Hubble Deep Field showed us thousands of galaxies in a tiny patch of sky. Extrapolating to the whole sky, astronomers estimated 200 billion galaxies. More recent studies, accounting for smaller, fainter galaxies, have revised that estimate to around 2 trillion galaxies. Each of these galaxies contains billions of stars. Some contain hundreds of billions. A few contain over 1 trillion. Multiplying the number of galaxies by the average number of stars per galaxy, we arrive at the total. Around 10 to the 23rd stars. 100 to 200 sextillion stars, a number beyond human comprehension. We explored the tools astronomers use to make these estimates: the mass-to-light ratio, star counts, statistical analysis, surveys from telescopes like Hubble, Kepler, Gaia, and the James Webb Space Telescope. Each tool has its limitations. Each estimate carries uncertainty. But the overall picture is clear. The universe is filled with stars. We discuss the different types of stars. Red dwarfs, the most common, small and cool and long-lived. Yellow dwarfs like our Sun, medium-sized and stable. Blue giants, hot and bright and short-lived. Red giants, elderly stars nearing the end of their lives. White dwarfs, the dense remnants of stars like our Sun. Neutron stars, even denser, the cores of massive stars that have exploded. And black holes, the ultimate endpoints of stellar evolution. We considered the life cycle of stars, born in molecular clouds, burning hydrogen for millions or billions of years, dying in various ways depending on their mass, scattering heavy elements into space, enriching the next generation of stars. A cycle that has been repeating for nearly 14 billion years. We explored the connection between stars and life. Stars forge the elements of chemistry in their cores: carbon, oxygen, nitrogen, iron. These elements are scattered into space when stars die. They become part of new stars, new planets, new organisms. We are made of stardust. The atoms in our bodies were forged in the hearts of stars. We discussed the dark side of the cosmos. Dark matter, the invisible substance that provides the gravitational scaffolding for galaxies. Dark energy, the mysterious force accelerating the expansion of the universe. Together, dark matter and dark energy make up 95% of the total energy content of the cosmos. The stars and planets and life forms that we can see are just a tiny fraction. We looked toward the limits of our knowledge, the cosmic horizon, beyond which we cannot see, the possibility that the universe extends far beyond the observable, the theory of cosmic inflation, which suggests the true universe may be unimaginably larger than the part we observe, the chance that the total number of stars is not sextillions, but infinity, and we reflected on what it means to count the stars. To be a small collection of atoms, on a small planet, around an ordinary star, contemplating the immensity of the cosmos, to be the universe looking at itself, to be matter that wonders. This is where our journey has brought us, not just to a number, but to a perspective, a way of seeing ourselves in relation to the cosmos. We are small, but we are connected. We are brief, but we are aware. We are limited, but we can imagine the unlimited. The stars will continue to shine whether or not we count them. The galaxies will continue to turn whether or not we observe them. The universe does not need our attention to exist, but we need the universe. It is our home, it is our origin, it is our context, and there is something beautiful about paying attention to it. Something meaningful about turning our gaze upward and asking questions. The universe may be indifferent to our curiosity, But our curiosity is not indifferent to the universe. We care about understanding. We care about knowing. We care about finding our place in the cosmic story. That story is far from over. The universe will continue for billions of years. New stars will form. Old stars will die. Galaxies will merge and evolve. The cosmic web will stretch and thin. Eventually, trillions of years from now, the last stars will fade. But that is far in the future. For now, the stars shine. And for now, we are here to see them. This moment, right now, is part of the cosmic story. You, listening to these words, are part of the cosmic story. Your thoughts about the stars are the universe thinking about itself. Your wonder is the universe experiencing wonder. So let the numbers settle into your mind. 100 sextillion stars, more than grains of sand on all the beaches of Earth, more than seconds since the Big Bang, a number that represents the generosity of the cosmos, its abundance, its vastness. Let the images settle into your mind. Spiral galaxies spinning slowly through the void, stellar nurseries glowing with the light of newborn stars, supernovae blazing brighter than entire galaxies for a brief moment before fading, black holes lurking in the centers of galaxies, their gravity bending space and time. Let the connections settle into your mind, the atoms in your body forged in stars, the light you see traveling across years and centuries to reach your eyes, the questions you ask, echoing the questions humans have asked for millennia. You are part of this. You belong to this. The universe is not something out there, separate from you. It is something you are made of, something you participate in, something you are. And the stars are your kin. Not in a mystical sense, but in a literal, physical sense. The same nuclear physics that powers the sun powers every star in the sky. The same chemistry that forms molecules on Earth forms molecules on distant planets. The same gravity that holds you to the ground holds galaxies together. The laws of nature are the same everywhere, and you are part of nature. This is the final lesson of our journey. Not just a number, but a relationship. You and the stars are related. You share a common origin, a common physics, a common cosmos. When you look at the stars, you are looking at family. So look, as often as you can, as deeply as you can. Let the starlight fill your eyes and your mind. Let the scale of the cosmos put your worries in perspective. Let the beauty of the night sky remind you of the wonder that is always available to those who take the time to notice. The stars do not ask anything of you. They do not demand your attention or your worship. They simply shine, as they have for billions of years. But if you give them your attention, they will give you something in return. A sense of scale, a sense of wonder, a sense of belonging to something immense and beautiful and ancient. And that is a gift worth receiving. A gift that costs nothing but a moment of your time. A gift that never runs out, no matter how many times you receive it. The stars are generous. They offer their light to anyone who looks up. So look up. Tonight and every clear night, let the stars be your companions, your teachers, your reminders of what is possible. Let them inspire you to ask questions, to seek answers, to never stop wondering. The universe is vast. The stars are numerous. And you are here, part of it all, able to appreciate it all. That is a rare and precious thing. That is something to be grateful for. Rest now. Let the numbers and images and ideas we have explored drift through your mind like starlight through space. There is no need to hold on to any of it. The stars will still be there tomorrow and every night after. The universe will still be vast. The wonder will still be available. Sleep and dream of stars. Dream of galaxies spinning and nebulae glowing and black holes lurking in the darkness. Dream of the universe in all its glory, and know that you are part of it. The count is complete. 100 sextillion stars in the observable universe. A number beyond comprehension. A number that tells us what kind of universe we live in. A universe of abundance. A universe of generosity. A universe that scatters suns across the void like seeds in fertile soil. And somewhere among all those stars, on one small planet orbiting one ordinary sun, a collection of atoms has become aware, has looked up, has wondered, has counted. That collection of atoms is you, and your wonder is the universe wondering about itself. Good night. The stars will keep watch while you sleep. The night deepens around you now, and the thoughts we have shared begin to settle like dust after a gentle wind. But before you drift into dreams, let us spend a few more moments together, contemplating the quiet majesty of what we have discovered. There is something almost sacred about the night sky. Throughout human history, people have looked up and felt a connection to something greater than themselves. Ancient astronomers in Babylon tracked the movements of the planets. Polynesian navigators sailed across the Pacific using only the stars as their guide. Medieval monks recorded the appearances of comets and eclipses. Renaissance scientists revolutionized our understanding of the cosmos. Each generation has added to our knowledge of the stars. Each generation has stood on the shoulders of those who came before, reaching higher, seeing farther, understanding more. We are the inheritors of this long tradition of looking up and wondering. The number we have arrived at, 100 sextillion stars, would have been unimaginable to the ancient astronomers. They saw only the few, 1,000 stars visible to the naked eye. They had no way of knowing about the billions hidden from view by distance and dust. They had no concept of galaxies, no idea that the fuzzy patches of light in the sky were vast collections of billions of suns. But they wondered. They asked questions. They tried to make sense of the lights in the sky. And in doing so, they began the journey that has led us here, to this moment, to this number. The tools have changed. We no longer rely on naked eye observations alone. We have telescopes that can see farther than our ancestors ever dreamed. We have spacecraft that can travel beyond the limits of our planet. We have computers that can process more data in a second than a human could process in a lifetime. But the wonder remains the same. The feeling of awe when you look up at a clear night sky is the same feeling our ancestors felt. The questions we ask are the same questions they asked. How many stars are there? How far away are they? Are we alone? These questions connect us to all the humans who have ever lived and wondered. They connect us to the future generations who will continue to wonder after we are gone. They connect us to the universe itself, which seems almost to invite our curiosity, to reward our attention with beauty and mystery. The stars do not answer our questions directly. They simply shine, but in that shining, there is an answer of a kind. The answer is that the universe exists, that matter organizes itself into stars and planets, that light travels across vast distances to reach our eyes, that we are here to see it all. This is enough. This is more than enough. The fact that we can ask questions is itself a kind of answer. The fact that we can count the stars is itself a kind of miracle. The universe has produced in us something capable of contemplating the universe. What more could we ask for? And so we count. We measure and calculate and estimate. We push the boundaries of our knowledge further and further out into the cosmos. We discover new galaxies, new stars, new planets. we find that the universe is larger and more complex than we ever imagined. And at the end of all our counting, we arrive at a number that humbles us: 100 sextillion stars, a reminder that no matter how much we learn, there is always more. No matter how far we see, there is always farther. The universe has depths that we will never fully plumb, but we can appreciate what we can see. We can marvel at what we can count. We can feel gratitude for the opportunity to be here now, alive and aware and wondering. The stars are calling you to rest now. Their light, ancient and patient, falls upon your closed eyelids. The numbers we have discussed settle into your unconscious mind, where they may inspire dreams of cosmic voyages and endless horizons. You have traveled far tonight, further than any spacecraft has ever gone. In your mind, you have visited distant galaxies and counted their stars. You have witnessed the birth and death of suns. You have contemplated the fate of the cosmos across trillions of years. And now it is time to return to this small planet, this quiet room, this moment of rest. The universe will wait for you. It has been waiting for billions of years. It can wait a little longer while you sleep. Tomorrow, the stars will still be there. The number will still be 100 sextillion. The wonder will still be available to anyone who takes the time to look up and think. For now, let go. Let the vastness of space become the vastness of sleep. Let the light of the stars become the light of dreams. Let the questions we have asked become the seeds of new questions, new explorations, new discoveries. You are a child of the cosmos, made of the same atoms as the stars, part of the same story that has been unfolding for billions of years. Rest now in the peace of that connection. Rest, knowing that you belong to something immense and ancient and beautiful. The count is complete. The journey is over. The stars shine on, as they always have, as they always will, keeping watch over a sleeping universe that has, in you, awakened to wonder. Good night. As the silence of the night wraps around you, one final thought remains. Of all the sextillions of stars in the observable universe, only one has warmed your face. Only one has grown your food. Only one has lit your days and marked your years. Our sun, that ordinary yellow dwarf, is the most important star in the universe to you. Not because it is special, but because it is yours. And around that star orbits a small blue planet where atoms have learned to think, to love, to wonder. This planet, this Earth, is rare and precious in ways we are only beginning to understand. It may be one of billions of habitable worlds, or it may be unique. We do not yet know. What we do know is that it is home, the only home we have ever known. A tiny boat sailing through the cosmic ocean, carrying its cargo of life through the darkness between the stars. The stars we have counted tonight are all at immense distances from this small boat. The nearest is over 4 light years away. The farthest visible to our telescopes are billions of light years distant. We cannot visit them. We cannot touch them. We can only see their light, ancient messages traveling across the void. But in seeing them, we participate in them. In counting them, we include them in our understanding. In wondering about them, we extend our minds across distances our bodies could never cross. This is the magic of consciousness. This is the power of thought. You carry within you a model of the cosmos, a mental map of stars and galaxies, of distances and numbers, of births and deaths and endless transformations. This model is incomplete. It always will be. But it is yours. It is your way of participating in the universe, of being a part of the cosmic story. And the story continues. New telescopes are being built. New observations are being made. New discoveries are on the horizon. The number we have discussed tonight, 100 sextillion stars, may change. It may grow larger as we detect fainter galaxies. It may be refined as we develop better methods. But the essence will remain. The universe is vast. The stars are numerous. We are small but aware. These truths will persist no matter what future observations reveal. So carry these truths with you as you sleep. Let them be a comfort and an inspiration. The universe that contains so many stars also contains you. You are part of its fabric, woven from the same threads of matter and energy that make up the most distant galaxy. And when you wake, the stars will be waiting. Perhaps hidden by daylight or clouds, but still there, still shining, still offering their ancient light to anyone who takes the time to look. 100 sextillion stars, each one a sun, each one a story, each one a part of the vast, beautiful, mysterious cosmos that is your home. Sleep now. The stars are keeping watch, and in your dreams, perhaps, you will count them again, walking among them like an explorer in an infinite garden, marveling at each bright flower of fusion that blooms in the darkness of space. The journey is complete. The number is known. 100 sextillion stars, give or take, in the observable universe, and you, made of stardust, dreaming of the stars that made you. Peace, rest, wonder. The universe embraces you. Good night.